All right. So, so over the past several classes that we've had, I would say past several weeks, but with how intermittent that these classes have actually been, it's been the past several months more like it. But most of the stuff that we've been working with is, audio files and actual, recorded clips of either audio that we've either recorded in class or we've just found samples of or manipulated and stuff like that.
Hmm.
Now we're getting into the stuff where we're going to be talking more, the nebulous kind of man-made sort of sounds rather than stuff that we go out and record ourselves, which we're going to get into like the basics of, how synthesis necessarily works. So the first thing that I have is, what is synthesis? Synthesis, most of the definitions for this class are my own definitions, like of how I interpret most of this stuff, because I don't want to like copy and paste stuff from the internet because I feel like that doesn't feel genuine. But the way I feel that it is, and synthesis means different things in different disciplines, whether you're talking about, synthesis of, stuff in, biology or in chemistry. It's essentially, combining various elements together to create something new. And with synthesis of music, we're essentially combining various musical elements together through what ends up being through circuitry and stuff like that to create various sounds. So, the base term of synthesis is synth, which is synthetic, artificial, man-made stuff that, doesn't exist in nature. So that's why a lot of people, when they talk about, different synths or different presets or different patches or different things that they hear that are synths, it mostly people can describe it to be, it doesn't sound real. It sounds either, you know, like a robot, or it sounds like fake, or it doesn't sound like anything you've ever heard before. And that's the kind of thing that you can get with synthesis is, we have this standard set of, hundreds of different instruments, many of which are standardized through, if we're talking, Western classical music of, we have the orchestra, or we have, what we consider, most instruments today is of like guitars, drums, all of these things that are standardized. But with synthesis, you really break out and be like, okay, what kind of sounds can we make that are not acoustically, available in the real world? So that's essentially what synthesis is we're creating something on our own. And it could sound like something you've never heard before, or you can use it to try to make or remake an acoustic sound and replicate that. So the next question I have is, what is a synthesizer? So synthesis, synthesizer, it's mostly just a device, and it can be a physical hardware device, or it can be a virtual device in the computer that produces man-made artificial sounds. And there's a bunch of different types of synthesizers out there made by a bunch of different companies, and they don't have to look exclusively like this. There's a bunch of different synthesizers that don't have a keyboard, or are just completely knobs or whatnot, or they use a different kind of control surface altogether. So in the grand scheme of it all, a synthesizer is essentially something that creates an artificial sound, something that produces a sound using, various circuitry. And I'm kind of going quickly through, the different types of synth stuff before we get into like the main meat of it, because everyone knows what a synthesizer is, but I have to explain like, what is a synthesizer, what is synthesis, and what are the different uses that you can get out of it. This is an example of like a control surface that's not a keyboard. It's essentially, you would touch your fingers to this, and you would create different electrical paths across these different surfaces here. So you can use synthesizers. A lot of people use it for music, whether it's, where it got its start in like the 70s, 80s, using that kind of aesthetic, or you can use it in different kinds of sound design to create those different sounds that you want, that you wouldn't necessarily be able to get from, an acoustic source, or even manipulating that acoustic source to make it sound, otherworldly. And of course, you get synths used in TV, movies, and video games all the time to create that kind of effect. I just wanted to get that out of the way real quick because, everybody knows that, but it needs to be said when we're talking about what is synthesis in and of itself. But I'm not gonna lie, this slideshow is 40 slides, and I've been working on this all week, and I've assigned every slide a term that I feel like is important to know before getting into synthesis. And some of these terms we've already gone over in MRT2. They're basic physics terms of like what is the basics of a sound wave and stuff like that. And some of that stuff I'm going to go over quickly because I don't need to repeat what's already been said, and you guys already know most of what that is anyway. But you'll notice that something about all of these terms I'm about to mention is the fact that a lot of them are based in the world of electrical circuitry or physics. And that's mainly because of the fact that whenever, people started making synths, it was just people putting together different electrical components and then just taking whatever signal that they created through those electrical components and putting it out of the speaker to see what kind of sound that they would make. And a lot of what circuitry is, different types, just electrical physics or, basic circuitry terms. So that's mostly what all of these terms are going to sound like. So if you aren't, very well known, if you don't know a lot about circuitry or physics, some of this might go over your head, but it's important to know that there is that connection because synthesis is essentially, just a bunch of circuits put together. So the basic thing that we're going to go over, amplitude. Amplitude is how loud a wave is, how loud a sound is, and that's measured in decibels. Or there was something else that we measured, and I don't remember what it was, but and that's typically, and this is your typical waveform, and amplitude is the height of the wave, how far it goes above this middle line here. The higher it is, the louder the waveform is. And if you're in like the real life, you're going to be measuring amplitude in decibels, SPL. That's like what we know decibels mostly as the how loud we measure something in decibels. Or if we're working in a synthesizer or in a DAW, it's going to be dBFS, which is going to be calculated in bits, and that's going to be measured in negative numbers, where 0 is the loudest, and then it goes down negative from there. So amplitude is how loud or how grand the scale of it is. Frequency, again, basic terms, is the pitch of a sound measured in hertz or cycles per second. So how many times does it take for this wave to cycle through in 1 second? And the pitch or the frequency is also dependent on the wavelength of this particular sound. So if you have a shorter wavelength, you're going to fit more of those cycles per second in. We're going to fit more of those cycles in a second so that it's going to be a higher pitch. And if it is a longer wavelength, you're going to have less of those cycles per second, and then it's going to be a lower pitch. So higher frequency, shorter wavelength, higher pitch, lower frequency, longer wavelength, lower pitch. Again, these first couple slides I'm going to go through real quick, but there's going to be some slides down the line in which I'm going to talk a little bit more in depth on, like with waveforms. So we talked about, essentially how a sound is represented either through amplitude and frequency and wavelength and all that stuff. So let's take a look at how, the different shapes of a waveform. Now, a waveform can have different shapes. It's just what the wave looks like within a single oscillation. So a single oscillation would be it goes up and then down and then back to this middle line here. So basically taking one full circle 2 pi radians around the the center line here. You'll also notice that a lot of the terms when we talk about with this are related to trigonometry because of the fact that we have oscillations, which is a big thing in trigonometry. Is how do we measure that? How do we graph that out? So if you hear me use those kind of terms, that's because all of this is connected with that kind of discipline. And the shape of the waveform is going to determine, the exact sound of that waveform. So we have different shape waveforms here, and you'll notice that, they're all the same, wavelength, they're all the same amplitude, they're all the same frequency, but they have different shapes. So that means that they're going to have a different timbre to them. They're going to have a different tone to them. So these are the 4 essential waveforms, and we'll go through them one by one and go a little bit more in depth on them right now. So the first one that most people, or it's the most basic waveform, it's a sine wave. And again, if you've taken trigonometry, you've probably worked with sine functions and sine graphs as well. It's the same exact thing. It's the same function, and it's the most smooth and consistent. You can also call it a sinusoidal wave. That's the long name of it, but most people will just call it a sine wave. Most people will know what you're talking about. So it's the most smooth and it's your basic oscillation. It's going back and forth at a regular rate, kind of like a fan would go back and forth, an oscillating fan. It has a very smooth sound to it because it only represents one singular frequency. So you'll notice that if we look at this kind of EQ looking thing, it has a peak at one singular frequencies. So it doesn't have any, overtones or harmonics or anything like that. I don't remember the exact name of the scientist that I should have looked this up. The exact scientist. Oh, sorry about that. The exact scientist that looked up that created the theory about complex sounds, but essentially that they're made up of a bunch of different sine waves. All complex sounds are made up of individual sine waves. However many, there's going to be a lot of them, and they're going to be combined together. So if you look at right here, we have 3 different sine waves, and if we combine those sine waves together, we create all new wave shapes. So these wave shapes are basically, the sine wave with other sine waves added together to create a whole new shape, a new sound. And you can hear all these individual, harmonics together, but sometimes, there's so many harmonics in a particular sound that it just sounds like one fuller sound. And of course, the sine wave is going to represent, in most sounds, if you look at the first frequency, the lowest frequency of that sound, that's the fundamental frequency or the first harmonic. And then every other one over those will be second harmonic, third harmonic, or first overtone, second overtone kind of thing. So the sine wave is, your basic waveform, and it's really good for like basses. So, bass guitar sounds really similar to a sine wave, but also a flute sounds very similar to a sine wave. So it's not necessarily, strictly, one way or the other. But it's good to use as like a sub bass in your mix, or to use to affect it in different ways to create like an 808 sound. So the sine wave is the most basic of all of the different waveforms. And next, we'll go over a triangle wave. So triangle wave, you'll notice that the names of these waves, yes.
I have a quick question, if that's
Yes.
okay. Would you like me to give some aural demonstration of these different waves? Because I happen to have, okay, you have one,
I have that, and actually, thank you for reminding me, because I have my own demos to represent these sine waves. I forgot that I had that.
That's okay. I was going to share, that's why I took myself off camera for a second. I actually got out my phone and I was going to share my screen. If you want, I have my Arturia right here, and it's got all the different, so whatever, you do your thing. I just want you to know I have that resource. Just let me know if you want me to share. I'm
Thank you for reminding me about that. I actually, whenever I was testing this out with Zoom, much like other communication platforms, when they do screen sharing, do not do audio.
Yeah.
So I had to find a way to like patch in the audio using a third-party plugin. That's why there was that noise that started, and I had to turn that off, like, because I'm using a trial version of something, and they're like, "Hey, would you like to pay for it? Because if not, we're just gonna put a bunch of noise in the signal."
Okay, so, I will mute my mic. Continue. You're doing a great job.
Okay, thank you.
You're welcome.
So I just have a few different examples. So for a sine wave, I'm going to represent it as, I have 2 different demos per wave here. And for the sine wave, for each one, it's going to be, C4, and then I'm going to show like C3, C2, C5, C6. So just showing the sine wave played at different octaves so you can hear what they sound like in different contexts. So this is the first demo that I'm showing for this. So this is a sine wave. Oh, apparently not. Hopefully that's loud enough. So, but the next version, I wanted to show it not just like what it sounded like tonally, but I also wanted to show what it sounded like in a musical context. So I hope you guys are okay with me playing the Turkish March 5,000 times, because I'm going to be playing it with a bunch of different synths. So here's the Turkish March played with sine waves. Hopefully that sounded good enough. The thing is like I gotta keep it level. The sine wave is going to appear to be the quietest whenever I play it back because of the rest of them having more harmonics in them. So, but that's what a sine wave sounds like, and that's what a sine wave sounds like in context with music. Next, we'll get into a triangle wave. So you'll notice that all of these waveforms are just essentially named after the shape. So a sine wave was named after, the sine function. This is named after it being shaped like a triangle. So you can say that a triangle wave is very similar to a sine wave, even if you have them like layered on top of each other, they look very similar. But the thing about a triangle wave, when you look at it under, an EQ, is that you'll notice that it has different harmonics. More precisely, it has the odd harmonics. So you'll notice all of the different harmonics are represented here. So first, second, third, fourth. It represents all of the odd harmonics to the inverse square law of that particular harmonic. So if it's the third harmonic, then it's 1/9 of the volume of the fundamental, and then the fifth would be 1/25th, and so on. So that's the essential shape of a sine or a triangle wave under an EQ. Triangle waves, most of the time, the most probably famous use of a triangle wave is within the NES, its sound card, since the NES could only produce, very particular waves. It couldn't produce a sine wave. So the thing that they decided to go with is to use a triangle wave to represent the bass line of most of the NES songs. Because that's the closest thing that you can get. And you'll notice that it sounds very similar to a sine function, a sine wave form. So here is what the triangle waveform sounds like in different octaves. So that's what it sounds like, in the different octaves. Notice it sounds like kind of like a sine wave, but it has a little bit more edge to it, as because of those upper harmonics. There's not a lot of, well, there is a lot of them. That's all of the odd harmonics. But as those harmonics go up, they vastly go down in terms of amplitude. So you don't hear the upper harmonics as much. So here's a triangle wave in context with the Turkish March. So that's a triangle wave. Next, we'll go over a saw wave or a sawtooth wave. Both of these terms are interchangeable. You can use whichever one you want. But you'll notice that it's named a saw wave because of the fact that it's very jagged. It kind of looks like a saw blade, either at like the blade of a hacksaw or a chainsaw kind of look. Like it looks like if this was running really rapidly, it would do a lot of damage to some wood. And you'll notice that in this particular example, it's ramping up and then immediately falling down, ramping up and immediately falling down. You can invert the signal of this, so having it go down and then immediately up, down, immediately up, down, immediately up. You're going to get the same sound because it's essentially just inverting the phase of it. So it doesn't matter which way it goes, it's just going to sound, it's going to sound the same every time. And what you'll notice about a saw wave is the fact that it's very, very harmonically rich. You'll notice that all of the harmonics are represented. So every single harmonic is there, and it goes down at a lot slower rate. So there's a lot more amplitude in these frequencies right here. Like right at the ninth harmonic, it's only at 1/9, when back here it was 1/81st the volume of the amplitude of the fundamental frequency here. So again, and it's inversely, so it goes down by being inversely proportional. So so you have 2, the inverse is 1/2, 3, inverse 1/3. So it goes down at that rate. Saw waves are really good at really filling out that frequency spectrum because of the fact that it's very harmonically rich. There's a lot of frequencies going on here. And the fact that you can kind of layer these on top of each other really well to create what are essentially super saws. So those are saws that are like stacked on top of each other, saw waves stacked on top of each other, maybe detuned a little bit to really fill out the space of the mix that you're going for. And they can create really nice pads too. So sawtooth wave, whatever you want to call it, and it can be inverted. So it doesn't have to look like this. Very harmonically rich waveform, used a lot for mostly like chordal stuff, but it doesn't have to be. So this is what a saw wave sounds like. You'll notice it's a lot harsher than the triangle wave. It's got a lot more of those upper harmonic frequencies going on in it, and it really, expands the whole, frequency range. So here's the context of it in with Turkish March again. You'll notice that when you listen to that, it's like frequency wise, it sounds a lot more busy. Like some of the frequencies kind of are, conflicting a little bit with each other. And that's because there are so many of it. It is so harmonically rich. So that's the example of the saw wave right there. So the last basic waveform we're going to go over, I have a little bit of bias towards this one. It's the square wave. Also, people call it a pulse wave or a pulse width wave. It's the exact same thing. So if you see square or pulse waves, it's essentially this. It's shaped like a square or rectangle, depending on the amplitude. Obviously, if it's has a very high amplitude, it's going to look more like a rectangle, but essentially it's a square. It's shaped essentially like a square. And you can also kind of think of it, if you look at it, as being like on off, like binary. So if it's at the top here, you can consider that being on, and then it immediately falls down to being what you would consider to be off. There's not much middle ground here. It goes like almost immediately to one side or the other. So it has that binary aspect to it. So in a way, you can say that a square wave kind of is like a very distorted sine wave. So if you consider this to be like the ceiling of your sound, and it just has the sine wave going up and then immediately back down and then just hitting the floor or the ceiling, just can't go any higher than that, and then moving back up. So it has kind of a very distorted sound to it. And you'll notice here in the graph, it's the same as it's the same exact thing as the saw wave, but these even harmonics are missing. So square waves and saw waves are very similar. It's just that, again, sawtooth waves are very harmonically rich because they have all these even frequencies in here as well. The square wave does not have all those frequencies. But the thing about the square wave is that you can have different types of square waves, and that's going to be dependent on, the pulse width, as what it's called. So here in this diagram, you can see most square waves that you see represented are going to be the 50% square wave, and you can consider it being like 50% on, 50% off within a single, period here, within a single cycle, within a single oscillation, because it's 50% up, 50% down, and that has a particular sound to it. And then you'll notice like this is still a square wave, but has a different shape to it. It has, 30% up and 70% down. And here it's 10% up and 90% down. But the thing that you'll notice is like here we have a 10% square wave and here we have a 90% square wave. They're essentially just inverses of each other because you have 10 up, 90 down, you have 90 up, 10 down. They're just inverses of each other. They're going to sound exactly the same. So you don't really see too many people talking about anything over 50. You can if you want to, but most people are going to talk about 50, 25, 10, 12.5, whatever the width of this first hill is compared to the rest of the period. So I'm going to play first. I'm going to play a 50% square wave. So this is what most people would consider a square wave. And the reason why I also call it a pulse wave is because of the fact like you consider these like different pulses. So it's like pulse on, pulse on, pulse on. And it's like how much of the period is that pulse on. So it's on 10% here, 30%, 50%, 90%, and so on. So I'm going to show you a 50% square wave or a 50% pulse wave right here. So you'll notice it kind of has that saw wave sound, but it's not as, harsh. But it kind of has more of that, a little bit of, digital distortion sound. And then here we have the musical context for that. You notice that you could hear the melody really well. Like the melody really stood out there. And that's why a lot of times when people are making synths or they're making like the lead melody synths for something, they'll end up using, in some variation of a square wave or, layer it together with a square wave because of the fact that it has that very piercing quality. It has that nice melodic kind of sound to it. Even though it's organized the same way as a saw wave, it has less of those, it's not as harmonically rich, it has less of those frequencies, which means that it's not as busy, which means it can kind of stand out on its own a little bit more. So the next thing I'm going to show you is a 25% square wave. So it's 25% on, 75% off. Kind of looks like this, even though this is 30, but just imagine like 25% for this. So this is what 25% square wave sounds like. And then here is the musical context for that. And as I show you these variations of the square wave, this is for the 50%. So the EQ for a 50% square wave is going to look like this. The 25, 12.5, 10, 30, they're all going to look slightly different than this, but they're going to have the same kind of sound to it. And also, in case you're expecting, like, in case you're like, oh, am I supposed to, know what, am I supposed to be able to hear the difference between a 25% square wave and a 50% and a 10%? No one has that kind of a perfect ear where they can be like, oh yes, that is a 15.73% square wave. Yet, as long as you can tell that it's a square wave of some sort, you can, have that kind of oral skill to be able to be like, okay, I know that that's a square wave of some kind. So, and you'll notice that these kind of sound a little bit similar because they're all the same type of waveform, but they do sound different. That's the main thing. So the last thing I'm going to show you is the 12.5% square wave, and that sounds like this. And then here's the musical context. You notice a lot of these, basically all of these sounds that I've shown you sound very chiptune, and that's because, like the NES, what's it called? The Sega Master System, they only had 8-bit, sound cards, so they can only produce these basic waveforms. So this is the kind of, instruments that they were essentially working with, were these very basic synthesizers that could only produce these kind of waveforms. And you'll notice that, you've probably heard these different types of square waves before, but these are very simple to, work with in, those different sound cards. So last week we went over noise. So we talked about the different colors of noise, and we talked about, sampling noise and how that could be useful in terms of, layering that on top of your acoustic sources. Well, a lot of synths allow you to be able to layer noise on top of your synths. So we'll talk about it again. Noise is essentially, represents all of the different frequencies across the different frequency spectrum because of how random the waveform is. And there goes the random noise. Speaking of noise, we got the noise coming in from my trial program. But we have different colors of noise that we talked about last week. White noise being very flat, pink noise decreasing 3 decibels per octave, having a lot more lower representation than higher. Brownian, brown, and red noise, all the same thing, even more so. So that's decreasing by 6 decibels per octave, a lot more of the low end. And a lot less at the high end. Kind of sounds like, what a lot of people would think of as background noise whenever they play it, like if they record something on a microphone and they have that noise in the background. It kind of sounds like this Brownian brown noise, but it can also be used to sound like, waves crashing in the distance for, people are trying to sleep, for different therapies, like kind of that. Blue noise essentially being the opposite of pink noise, increasing by 3 dB per octave. Violet being the opposite of brown. These have a lot more higher frequency representation. Again, I talked all about this last week. And then gray noise, like I talked about last week, is what human beings, the waveform that would result from how human beings' perception of a white noise signal would sound. So it has that, that weighted A inverse Fletcher-Munson curve. So a lot of the mid frequencies are lowered a little bit so that, to our very biased ears, it sounds like all of the frequencies are represented. Because when we listen to white noise, we definitely hear a lot more of the upper mid and the higher frequencies because they just stand out to us more. But with the gray noise, those frequencies are ducked out a little bit so that we can play gray noise and we would perceive it as what white noise actually is. So again, a lot of synthesizers will use noise generators, so you can add that into not only your acoustic samples, but also your synthetic samples as well. So now we're going to be getting into the terms used on basically every synthesizer that you'll ever see. So all of these terms are, the basic essentials, the different parts of a synthesizer, or the basic terms used for a synthesizer, and what makes a synthesizer, and that's going to be an oscillator. Some programs will call it, or some synths will call it, an operator. Some synths will call it a VCO, or a voltage controlled oscillator or operator. You can see here it's called an oscillator, here it's called an operator. This is a basic circuit diagram of it if you're interested in circuit diagrams. But essentially it's the component of a synthesizer which will generate the waveform using voltage if it's a hardware synth. Obviously a digital synth isn't going to create voltage in an oscillator, but it will replicate that, essentially creating that voltage, that waveform, that electronic, the electric voltage of the waveform. So this is the essential part of a synthesizer that, this is your source. This is your sound source. And you can use different, and you can see here the different shape. So you'll notice we have a triangle wave, we have a saw wave, we have the different forms of a square wave. You can be like, oh, I want a 50% square wave, or I want all the way down to like a 10% square wave. And you can figure out how much you want with that there. And of course, with these, you have your different shapes as well. So Oscillator is essentially, the thing that oscillates. It creates an oscillation in electrical current that essentially, is a vibration, and that we represent or we can, hear if we hook it up to a speaker as sound. So this is the device in a synthesizer that creates the essential basic waveform. So instead of getting that from, a recording, an acoustic source, this is the device that is creating your waveform. So, and you can create many different types of waveforms with it, and you can, mess with it as much as you want within the basic settings that you have in these things. And we'll talk about that as we go along. So before we go along, I want to talk about with synths, the difference between analog and digital synths. So analog obviously is, produced by hardware and you get essentially working with voltage. And that's how the original synths were, because people were just essentially putting different electrical components together. Digital is produced in a software. So it's going to just use, ones and zeros to be able to convey that information. And with analog, it can't represent the actual waveform perfectly because of the how limited actual physics is. It can't create something perfect like this using voltage. But, and with a digital thing, it can create it with a digital source. It'll create it pretty close. It's not going to be perfect, but it's going to be a lot more closer than it would be with an analog signal. Does that mean analog's bad? Not at all. Because with an analog synthesizer or an analog, anything, you get a different kind of sound out of it. You probably hear, rumors of people saying like, oh, analog gear sounds better or it sounds warmer. Well, there's a reason to that, because it's using voltage instead of, digital, code. It's only working with what it really can do based on actual physics. So a lot of people say analog gear has warmer tones to it. It sounds a lot more full. It has a smoother and more calming kind of feel to it, while digital is very, grating, very hissy, very just like aggressive. So depending on, and of course there's actual synthesizers, or there's digital synthesizers that replicate the sound of analog synthesizers and try to replicate that, very warm analog feel. But again, they're working with code. So that's the main difference that I wanted to talk about with the difference before we get into anything more intense with, terminology here. That's basically what this entire lecture is going to be, is terminology. But I wanted to talk specifically more about how there is a difference between how analog gear and digital gear sounds whenever you're working with it. So if you're wanting, a different type of tone, you might choose to go over analog or digital. It all really just depends. And also convenience is typically why people pick one over the other, or, whatnot. But I just wanted to talk about this real quick because of the fact that, it's important to know that there is a difference between analog and digital in terms of synthesis. So we have our oscillator. So the first thing, we have our oscillator. We have the thing that creates the noise, but it's not going to create noise on its own. Well, it can, but we typically want to have control over that. We want to send that oscillator information so that it knows what frequency to play. And what we can do to do that is send some kind of trigger from either, some kind of MIDI controller or CV controlled device. And we'll talk about MIDI and CV and gates immediately after this slide. But essentially an oscillator needs some kind of a trigger so that it knows what it's doing. It doesn't have to, you have some synthesizers that are just there producing, they're just oscillating, that are just producing an electrical signal, and it just is what it is. And you can modify it within the oscillator's parameters by, turning a knob or something. But typically in a musical context, we want to have control over that with either a keyboard or other sort of, device like that. So we would have either MIDI, control voltage, CV, or some other type of gate to be able to control the way that the oscillator reacts. So let's talk about MIDI. We're kind of going backwards in time by talking about MIDI, but MIDI is typically what a lot of people, associate with modern synth tech whenever they're talking about digital synthesis, because of the fact that MIDI, musical instrument digital interface, is a digital format. It's completely digital. So it's a protocol that is used to encode note information so that the synthesizer, so that the oscillator can essentially get information, be like, okay, so we're playing this pitch because that pitch means that we're playing this note. MIDI is a universal language, so a lot of, pretty much every synthesizer that you'll ever encounter, whether it's a digital synthesizer or an analog synthesizer, will be able to take some kind of MIDI source. Not all, but typically, commercially available, or people, stuff that the regular person can be able to get online or in a store, will be able to have MIDI capabilities in it, where you can have that digital signal go to the oscillator and say, this is what note we're playing, so do what you need to do to be able to do that. And the oscillator is like, okay, I have this information, I will play this frequency because that is equal to this pitch. So let's talk about a more analog version of it, in which we have control voltage, which you'll often see, abbreviated to be CV. And that's an analog signal that contains note information. And usually, and what it is just variations in voltage. And it could just straight up be like a frequency. Like you could send, because control voltage is voltage. And a lot of what we're working with here is voltage. What the synthesizer is producing and working with is voltage. So it's a wave itself. Like control voltage, if you plug that into a speaker, it's going to create a tone because of the fact that it's the same thing as your audio signal. So control voltage is essentially you just sending into the synthesizer, this is a wave that is telling you what note to play. And it can be controlled by, and you can have the CV be, you can have, the output of a synthesizer, like it creating a sound, plug that into a different synthesizer, and that's essentially your control voltage. Like you're telling that other synthesizer, hey, this is what you should be playing. And the other synthesizer's like, cool, because it doesn't distinguish between audio and control voltage signal, because it's the exact same thing. It's voltage. It doesn't really care. It doesn't be like, oh no, that's an output from a different synthesizer, I'm not going to listen to that. It doesn't matter. You can use control voltage however you want, in whatever crazy or creative ways that you want to do it with. So, but typically whenever you have, a keyboard, it's going to just send some kind of a signal, some kind of a voltage to a synthesizer, and it'll say, play this note. And that'll be in the form of analog voltage. So the last thing we'll talk about is gates. Both of these are essentially, gates in some way. Whenever you play on a keyboard, you turn the gate on, and you can send information to, the synthesizer. That's essentially what it is. You're opening the gate so that information can be sent to the synthesizer. And that can be in the form of control voltage or MIDI. Probably should have put this first, but I was working with the order of this slideshow so much, and it can control, various different things. Gates can control more than just the pitch. It can control the velocity of the note. It can control whether, if the note has vibrato or tremolo or aftertouch, if you're going for a more modern MIDI effect, various different things that you can control with a gate. So let's talk about like a little bit of the nitty gritty stuff. And I'm not going to spend too much time on what a parameter is, because it just kind of is very self-explanatory. So you'll notice whenever you're working with a synthesizer, it has a bunch of knobs or attenuators or potentiometers or, controls. And all of those controls are based on numerical values or some kind of measurable factor that you can be able to, that essentially is giving, whatever control you're saying, it's defining that particular control. So if we're talking with an oscillator and we're turning the knob to change the waveform, we're changing that parameter. Or if we're changing the volume of that oscillator, we're changing that parameter. So essentially it's any knob or controllable factor on a synthesizer. It's anything that you can control, anything you can change. And the reason that I mention this is because, as we'll get to later, you can have the synthesizer change its own parameters. You don't have to change the parameters of what the synth is. You can have the synth change those parameters for you to create different sounds. So going off of that, let's talk about what modulation is. So modulation, if you've taken enough, music theory to be able to get to the point where we're talking about, modulations in terms of key changes, modulation is essentially, if broken down to what it essentially is, it's just change. You're modulating something, you're changing something, you're modulating to or changing back and forth. So, and it's an effect that's used to change the parameters of anything within a synth. So when we talk about modulation, we have, the concept of a carrier and a modulator, or a modulating wave. The carrier is a constant waveform. This is going to be, this is going to be something that's just pretty much constant. That's, a basic waveform that just straight up constant. Or it could be like, say this is your wave that the oscillator is creating. You can have a modulator, which could be, and we'll talk about different types of modulators as we go on here, that can modulate that wave, that can change the way that wave sounds. And we have various types of modulation. Mostly, we talked about amplitude and frequency modulation. Amplitude modulation, so say if this is the modulating waveform, if we say that this is the amplitude that we want to modulate, well then the wave's going to get louder and then quieter, then louder and quieter. So we're modulating how the amplitude, or how loud that this basic wave is over time. We're not changing pitch, because you notice that it still kind of has the same frequency even though the amplitude is changing. The only thing we're changing is how loud the wave is over time. And the same thing with frequency. If we're saying that this is the modulating waveform for frequency, we're saying, okay, so it has a higher frequency here and has a lower frequency here, and you can see that here. The amplitude is not changing. It's still the same loudness, but you can see here it's getting higher in pitch, and then lower in pitch, and then higher in pitch, and then lower in pitch. So we're essentially using a different thing, and we'll talk about what those different things can be in a sec, to change this waveform. And this is essentially how you get into, the nitty-gritty of synthesis. This is what synthesis really is you using different waveforms or different shapes to change already existing shapes. So you'll notice that we talk about amplitude modulation, frequency modulation. You can call that AM and FM. Does that sound like anything familiar? This is how radio signals are also sent. So we have amplitude modulation, frequency modulation. Most people listen to FM radio, so this is how it works. We have to send out FM signal or AM signal. So you have the original song that's being sent through, and then you have something that's changing that, which is the essentially the frequency of that radio station, or the amplitude of that radio station. So if you're tuning into 97.6, I don't know what that radio station would be, but if you're tuning into that frequency, you're tuning into the carrier wave of that frequency, which is being modulated by the frequency wave of that song. I'm pretty sure that's how that works. If I'm wrong, I'm sorry, but it is using AM and FM modulation. That's essentially how it's working.
I have always wondered that, so I'm not sure. I'm going to take your word for it.
So I know that it is frequency and amplitude modulation.
Right.
I know that's what AM and FM stands for.
Same.
And so whenever you're tuning into a frequency, you're tuning into what the frequency of that carrier wave is.
Right.
So say if that's that,
right.
And then they're mixing that signal with the audio that's coming out of the radio station, and then your radio is just reverse engineering that to remove the carrier wave, and then gives you just the song information.
That sounds right to me.
That's how I've interpreted it.
Yep, that makes sense. That makes perfect sense. This is great. Keep going.
So yeah, that's essentially and it doesn't have to just be used in radio. We can use it in a lot with synthesis with different types of modulators. So let's talk about one type of modulator, a filter, also known as, it can be called a VCF, or a voltage controlled filter. And it's essentially an effect that's used to sculpt your synth sound in terms of frequency. So you can have, you have your basic low pass filter, which means that you're removing the high frequencies and only letting the lows pass through. So low pass filter, the lows are passing through. You have your high pass filter where you're cutting off the low frequencies and you're letting the high frequencies pass through, high pass filter. Band pass frequency, which essentially is you are defining a band of frequencies and letting those pass through. So letting those be the only frequencies. So cutting off higher frequencies past a certain point and lower frequencies past a certain point. Or a notch, you can also call this like a band reject filter as well. They have different names. But you can also call it a notch, which is essentially the opposite of a band pass filter, where you're defining a band or a frequency and cutting that frequency out. This just sounds like me talking about an EQ. I am. Oh, here we go again. Sorry about that. Because I am talking about an EQ. And essentially, every synthesizer has an EQ on it, but it's not the same as an EQ that you put in your signal path whenever you're working on a mix. This can change. You can have this change to be able to create different sounds. So you can have a low pass filter change over time to let more frequencies or less frequencies through. Same thing with a high pass filter. With a band pass, you can have it so that it modulates different frequencies, different bands of frequencies over time, or maybe more of these frequencies or less of these frequencies. So the thing about a filter is, yes, it's an EQ, but typically, you might have it in the sense that it is an onboard EQ for most synthesizers, but you can also have it be modulated by other different modulators. So let's talk about other different modulators. So we have an envelope. So an envelope is used to sculpt sound in terms of amplitude over time. So we had a filter which sculpted sound in terms of frequency, and envelope sculpts sounds in terms of amplitude. So filter, frequency, envelope, amplitude. And what we're working with here is typically this curve, which I've talked about before, is the ADSR curve, or attack, decay, sustain, and release. So whenever you have a synth produce a sound, or any sound, or if you have any sound, it's going to have an attack to it. And the attack is going to be how long it takes for the sound to go from absolutely nothing to its absolute peak loudness. How long is that quote unquote transient going to take? Because, it takes time to get from here where it's nothing all the way to its loudness. It's not automatically going to go to its loudness. It can get there very fast, like within, nanoseconds if necessary. And that's going to have a very, very quick attack time. And attack is determined in terms of time. So how long it takes to get there and how loud is it going to be. So how fast is it going to get to its loudest point, and what is its loudest point? So that's what the attack of an envelope is. Then you have the decay. So this is optional. You do not need to have a decay. You can just go straight to the sustain once you get to its loudest point and then just have it sustain there. But if you're wanting to have different types of articulation, so if you wanted to have more of an accented tone, or if you want to go for like bell tones or something like that, you can have the decay. And essentially what the decay is, it's the opposite of the attack. It's how long is it going to take to get to its constant frequency. So notice that during this whole time, the key that you're pressing on the synthesizer, or the signal that you're setting to the synthesizer, is consistent. So you're still setting a signal to the synthesizer, and at some point after it has reached its maximum point, it can reduce in amplitude over a period of time. if you want it to. So if you want more of like an attack and then have it, pull back a little bit after the attack and have a sustain at that point, you can do that. Or you can have like no decay at all and then it just goes straight to the sustain. So attack is time-based and amplitude-based. Decay is time-based and amplitude-based. Sustain is mostly just amplitude-based because it's going to sustain as long as you are holding the key, if that's how you define the synthesizer. So sometimes you can have a specific, you can define the sustain, say, oh, even if I'm holding the key down, I want it to move on to the release at this point. But for a lot of synthesizers, as long as you're holding the key, it's going to keep playing the note. So this is mostly going to be, amplitude based. So how loud are we going to be when we're holding the note out? And then the final part is the release. So at one point when we release the key, when we stop giving the synthesizer signal, how long is it going to take for that synth to go from its current point to absolutely nothing? So you can have that be like automatic, like as soon as you let go of the key, it stops. But you can have it have a little bit of a tail if you want to, where it kind of like, after you let go of the key, it's slow, it gets quieter over time. It doesn't immediately stop. So that's also amplitude and time based. So you'll notice that I've been mentioning envelope in terms of the amplitude of the synthesizer that you're talking about. And that would be considered the amplitude envelope. You can have many different types of envelopes. As long as you want to have a modulator that starts at a point and can be defined under these, procedures, and it has a start point and an end point. Like whenever you press down the key, it starts to affect the sound, and this can be in terms of frequency if you want it to be. It has a start point, it has a sustain point, and it has a release point when you let go of it. You can have a frequency envelope in that case if you want it to, or you can have this modulate other parameters. So say you want to go all the way to its max, but then pull back a little bit and then let go. It doesn't have to be in terms of, the amplitude of your sound. You can send this signal anywhere to modulate any parameter. And the same thing with a filter. Well, not really, but you can kind of do that. But mostly with an envelope, you're going to be sending a signal to a different parameter. Most of the time, you're going to see ADSR in how you shaped your sound in terms of loudness over time. Does it have a quick attack, or does it have a slow attack? Is it like a pad where it slowly fades in to its loudest point and then slowly fades out? Or is it kind of like a reverse sweep where it slowly fades in and then immediately cuts itself off? Or is it like, an impact sound? It has a very quick attack where it just has that impact sound, and then from there it just decays and then it falls off to nothing. So you can really shape how you want your synth to sound using an envelope, all dependent on how you define these parameters. And again, you can use this for other parameters to be modulated. So it doesn't have to be the volume. It can be, say you want to modulate what waveform you're using, and you have the waveform change over time. This is something that you can use for that as well. So the next modulator we're going to talk about is probably the one that people most associate with synths, and that's the low frequency oscillator. Most people will refer to it as an LFO. So an LFO, as it says, is a oscillator that generates a very low frequency. This frequency, most of the time, is either going to be a very low bass frequency, or it's not even going to be audible. Like you can have an LFO be 1 hertz, which means every second it oscillates once. So you might ask, well, if we have an oscillator that's playing a tone, a frequency that's so low that it can't be heard by the human ear, what is the point of it? Well, we're not going to use it in a musical context. We're going to use it as an effect. So say that you want to, because remember, when we combine waveforms together, we create different types of sounds. So even if we add a very low sine wave frequency to, a different sound, that sine wave frequency, even if it's 1 hertz, is going to, and let's say that we want to control the amplitude, we can have it so that it goes, we can use this oscillator to affect it so that we have a sine wave at 1 hertz. So our sound is going to go wow, wow, wow. So it's essentially modulating the volume of that particular parameter, and you can connect it to whatever parameter you want. You'll notice that there's a bunch of different parameters that you can connect it to, but essentially you're creating an oscillating effect that can be used to modulate a parameter, and it can be sent through CV or whatnot, but it's essentially going to be connected to a different parameter, and you can define the shape of the wave that you want, and how intense is that wave going to be. So the amplitude of that, is it going to be a very intense effect where it goes wow, wow, or is it going to be just very subtle, like wow, 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 wow. Sorry for my terrible vocalizations, but you get the point that I'm trying to say. Of the LFO can be used as a modulator to create different oscillating effects. So while to go back to the envelope, this is more of like a time-based one shot. So once it starts, it's going to go through its whole thing and then end. With an LFO, this is a constantly changing, so constantly oscillating effect. So this will constantly change over time. So these are the three, main modulators that we're going to be working with. So let's say, for example, that we wanted to have, let's say if we had a synth and we wanted it to, we wanted to have that oscillate, this LFO quality, that wobble, 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 where we get that wobble, wobble bass line kind of thing, like the wobble dubstep bass. This is where that comes from. And we get that wobble sound. But let's say that we want that wobble sound to change how much we want it to wobble. So like say we have a very consistent tone, and then as time goes on, or let's say we have a very wobbly sound, and then over time we want to change that. Well, we can use an envelope to do that if we want to. We can have it so that it starts immediately. So like attack is like immediate. And then from there, we can decrease how much the amplitude of that oscillation. So when it's affecting the other wave, it goes to a more consistent tone. So this is more of a one-shot time-based effect. So you can think of this as like a weird automation curve within the synth, while this is a constant back and forth effect that you can use. So those are the main modulators that you can use. The last thing that you're typically going to see when working with a synthesizer in your signal path chain is going to be the amplifier. Also, you can see it be called a VCA, or a voltage controlled amplifier. So we have VCO, voltage controlled oscillator, VCF, voltage controlled filter, VCA, voltage controlled amplifier. And essentially what this is the last part of your chain, of the synthesizer chain, in which it's when you take your signal after it's been modulated, after it's been filtered, after it's been mixed, whatnot, within the synthesizer, and it's going to go through the amplifier and become, they're going to amplify that voltage to be able to send it out of the synthesizer to a speaker, so that it's at a level that it can be sent out through a speaker. And typically when we talk about amp envelopes or the amplitude envelopes, this is usually the module of a synth where that gets affected, where you determine what is the ADSR, or what is the filter of that. And it doesn't have to be, but like this is typically like where your amp envelope is going to be. So this is the point where you get your audio input, you have your CV input from your envelope, and it's going to create that different sound. So this is essentially the last part of it. It amplifies your signal, sends it out of the synthesizer. So let's talk about some other maybe not nebulous, but some other terms. So a patch, if you've been in MRT3 or above, maybe MRT2, I don't know how the curriculum is designed now, but you probably have seen, you probably worked with patching in the control room, where we've taken cables and patched them into the patch bay into different things. That's essentially what this is. But with this, you are taking a cable. So a patch is a set of connections that creates a system of effects and pathways that define the characteristics of this synth. So these are very busy patches that I just found that I just thought were very funny to look at, but it doesn't have to be this complicated. What you're essentially doing if you're working with hardware is you're taking a cable and you're saying, I want to send this modulator effect to this parameter. So say if I want to take an LFO and modulate the volume of this oscillator. So that's what all of these patch cables are doing. They're sending modulation effects, or they're sending an audio signal to different modules within the synth so that it can create what is essentially the sound that the synth artist is wanting to create. Usually with most synths nowadays, you're going to be connecting with 3.5 millimeter cables. Sometimes it's going to be 1/4 inch cables, but usually it's going to be like 3.5 millimeter cables. And these are physical cables. These are your actual pathways. So when we talk about, gates and CVs going, from the synth, or going from the keyboard into the synth, or going, different signals being modulating other signals, this is how that's done. It's done through these different cables that are sending that information or sending that modulation signal to different things to tell, these different parameters to do what you want them to do. So that's a patch. So whenever you have, so what you're doing is you're essentially taking cables and patching them different places. And whenever you've completed your synth, the sound that you want to make, whenever you've completed your synthetic tone that you want, the layout of those pathways that you've created, the whole thing is called a patch. So that's your patch. That's the patch you've created to create the sound that you're making. So this is mostly in terms of hardware. If we talk about software, you can also have patches in software, but mostly people, when we're talking about virtual synths, are going to talk about presets, or you create a patch and make it a preset. So a preset is essentially, a patch. It's a virtual patch that you create and you save in the synthesizer. Now, this can be in the form of a virtual synth, and we have many different, presets here. Or it can be even on a physical hardware synth, different. If you go into like the lab, we have the Clavinovas, and they have a bunch of preset instruments on there that are all synthesized instruments. So they're called presets. So usually when we're talking about virtual synths, we use the term preset, or you can call it a patch. It doesn't really matter. It means the same thing, but you wouldn't really call, when you're working with physical hardware, you wouldn't really call that a preset. You would mostly call that a patch. So it's kind of interchangeable in the virtual world, but in the physical world, you would call it patch. Doesn't really matter how you call it. I'm just giving you the different terms that things are called. So we've gone over the basic terms of a synthesizer. So I threw a lot of terms, I threw a lot of different concepts at you guys, but none of this will make any sense unless I physically show you what a synthesizer, looks like, what the different parts of a synthesizer are, what is the signal flow of a synthesizer. So as we can see in this diagram, it's a little complicated, but I think what we can, no, I'm not, this is a circuit diagram. I'm not showing you, a circuit diagram. I'm not going that crazy with it.
Can you send that to me? Please, because that's really cool.
Yeah, I'll send that to you. I haven't actually looked over this. I just typed in like synth chart, and it just came up with this, and I'm like,
I
How
totally
do I
want to look at this.
how do I explain this? So I looked at a lot of charts online to try to explain what a synthesizer is, like the layout of a synthesizer. So the problem that I had when I was trying to find a diagram of a synthesizer was I either found this kind of stuff where it was overly complicated, or I found stuff that was way too simple, as in it didn't really cover everything that I wanted it to, or it just was very, basic, And there were some diagrams that covered what I wanted it to, but they didn't. It's either that they didn't phrase it the way I would have wanted to say it, or it just looked ugly and I didn't want people to look at it. I mean, so what I decided to do is I made my own diagram. I made my own flow chart to explain this, because I can't trust the internet to make anything consistent. Because if I look up a bunch of different charts on the internet, none of them are the exact same. There's no standardized way of looking at this, because here's the thing about synthesizers. None of them are the exact same. Every synthesizer is designed in its own way to make it unique. And that's the great thing about synthesizers, is that you can get whatever synth you want that fits your style. But that's what sucks about synthesizers, because every time you pick up a synthesizer, you have to try to figure out how it works, because it's not laid out the same way. So I thought I would just break it down into the simplest terms of what I've talked about here today. So as you can see, we have a keyboard, and we have speakers, we have a synthesizer. The goal here is to take notes from the keyboard, put it into the synthesizer, and make a sound out of it. So how do we do that? Well, first we need to plug in the keyboard into the synthesizer. So the keyboard is going to send either that MIDI or that CV signal, whatever it decides it's going to send, into the input of the synthesizer. Very simple. We're taking the output signal from the keyboard, putting it into the synthesizer. Next, that signal is going to go to, it's going to be processed, and it's going to go, made information by this. The synth is going to, take that signal, encode or decode it, and then send it to the oscillators. Now, I have two oscillators here. Some synths have one, some synths have 16. But most of the time, you're probably going to see 1, 2, 3, maybe 4 oscillators within a synthesizer. And what it is you'll see here that the signal is going to be split evenly between these two. It's going to be split and made parallel between all of the different oscillators. So the same signal that's getting to this oscillator is the same signal that's getting to this oscillator. So from here, from the oscillators, you're going to pick, what do you want your waveform to be? All of that information you're going to pick, you're going to figure that out in the oscillator. You're going to determine that information. From there, that signal is going to go into a mixer, both of these signals. So you're going to essentially combine these signals together into one waveform. So, and if it's with two oscillators, a lot of synths will have like a single knob to mix between them. So if you have the knob more towards one way, you'll have more of this synth than that synth. If you put it all the way one way, it's going to have, this synth, but not that synth. Usually in the synthesizer, you can also choose to turn off or on an oscillator. So if you only want one waveform, you can turn off, oscillator 2, only use oscillator 1, or you can just completely mute by like turning down the volume of oscillator 2. But essentially the mixer is going to combine those signals together into one singular waveform that can be worked with the entire synthesizer. From there, you're going to go into the filter. So if we remember what the filter is going to control and sculpt the sound of that particular synth in terms of frequency. So this is going to be our EQ. It's essentially going, straight from the oscillator, combine the signals together, and it's going to go into what is essentially an EQ. We're going to call it a filter because that's what everyone calls it, is a filter. And we can do your basic different types of filtering here. You can have your high pass, your low pass, band reject, notch filters, shelf filters, whatever you want. You can have, but a lot of different synthesizers have like fancy different filters like comb filters and all that kind of stuff. So have fun experimenting with like the different kinds of sounds that you can get out of a filter. And we'll talk about all of this more in depth next week when we actually get into working with an actual synthesizer or actual synthesizers. So, but it's going to go signal from keyboard into the oscillators. That signal is going to be combined back together in some way through the mixer, and it's going to go through the filter to basically EQ the sound how you want it to be. Next, it's going to go through an envelope that's going to determine the amplitude of that sound. So what was the envelope? What was the amplitude envelope? Well, it determined how we sculpt the sound in terms of loudness. So that's our ADSR. Is it going to have a quick attack? Is it going to have a very slow attack? Is it going to release immediately? Is it going to have a very long release? And we can determine the different parameters of that by saying, oh, the attack time is like 1 millisecond, which means that it's going to be like very, very transient heavy. It's going to be very loud at the front of it. Or we can say, you know, our attack time is 2 seconds, where the sound will go from its quietest point to its loudest point in 2 seconds. So you can really sculpt how you want your sound to, you know, the feeling of your sound really a lot with this particular module in and of itself, because of the fact that you're determining, you know, how does this sound behave over time in terms of its attack and its release and how it sustains. So, you know, if you want a very like heavy attack, you know, make it a quick attack. If you want it to be like a long, loving pad, reduce the attack or make the attack time longer, make it happen over a longer period of time. So you can really get the character of the sound that you want with the envelope here. Then we have our amp, our VCA, our voltage controlled amplifier. And again, this would be a VCF and these would be VCOs. But typically you'll see it mostly be seen as an amp or a VCA. You usually just see it be called a filter, and these just usually be called oscillators. But you know, these you will see VCA a lot more in terms of the amplifier here. And what that's essentially doing is it's taking your signal after it's, you know, been combined through the mixer, run through your EQ filter, and then been determined like its amp envelope. It's going to go in here and it's going to amplify the signal so that it can be sent out to the speakers through voltage. So yeah, that's the very basics of how a synthesizer is laid out. You have the signal going from the keyboard to the oscillators, and you determine the waveform of those oscillators and the phase of those oscillators, whatnot, yada, yada, yada. And that gets combined into the mixer however you want. Maybe there's more of oscillator 1 than 2. Maybe there's more of 2 than 1. Maybe there's more of oscillator 7 than 16. I don't know. It depends on the synthesizer. But then it's usually going to go into the filter next, where you can filter out certain frequencies. Then it's going to go into the amplitude envelope, where you can determine, you know, how it behaves over time. And then it's going to go into the amp, which is usually in most soft synths is going to be determined, it's just going to look like a volume knob. But in like analog hardware, you can determine a lot more with this. And then that's going to be sent out through voltage. Very simple, right? But remember, we can modulate almost any parameter in a synthesizer with those different modulators that I talked about. So what does that look like? It looks like this. So you notice that I have like these dotted lines. These are not your main signal. This is not like the signal that's going through the synth. This is modulation signal. But it, you know, it's the same thing, right? Because it's just voltage, but it's doing a different thing. So you can see the main signal is represented by the solid line, and then the modulators are these dotted lines. And these modulators are different types of envelopes. So you can have, you notice we have the amplitude envelope, but you can have different envelopes that do different things. You can have the envelope modulate the mixer. You can have the envelope modulate the filter. You can have another envelope modulate the amp if you want. I don't know, you do you. This is your synth, man. You can have it modulate the oscillators, either one or both. You do you. And then the same thing with the LFOs. You can have it excuse me, sorry, you can have the LFOs, modulate these different parameters over time too. So remember, envelopes are like your one-shot events, and then LFOs are your constantly changing events. So, but how do we determine, but you notice that like when we were talking about a keyboard, I'm sending MIDI and CV signal, but like if you hit a key harder, it's going to have a louder sound to it. Or, there's a lot of information that we can control from the keyboard to the modulators. And we do that with a gate, and usually this gate signal is going to be sent through the same wire that the MIDI and CV signal is, or if it's a MIDI signal, it's going to be sent through the same wire. If it's a CV signal, it's going to be sent through a different wire. But essentially, you can have control over the modulators from, the keyboard with a gate. So this is the basic layout of a synthesizer. Is this going to help you in determining how a synthesizer works? At first, no. And I say that because every synthesizer is laid out completely differently. And, some synthesizers might not have a filter. Some synthesizers might not have some of these things. Some of these synthesizers are going to have 5,000 other buttons that you'd have no idea what any of those mean. But these are the essential elements. And this is usually how it's going to be set up. Is it always going to be set up like this? No. Is it going to be set up like this most of the time? Probably. I don't know, but that's what's hard about this. That's what's hard about, really explaining this, is because of the fact that, there's no standard. There's no standard for how synthesizers work. It's just crazy people that have circuitry that just put them together however they want, and then they sell it. There's no standard. There's no, you have to follow this pathway. But for the synthesizers that we're going to be looking at, they're mostly going to follow this. Are they going to be laid out like this? No. Are the pathways going to be explicitly told to you? No. So you really just have to know that the oscillator is where the signal is essentially going to be created. It's going to go through a mixer. It's going to go through the filter and the envelope, and these can be switched. That happens sometimes. And then, but the main point is that these modulators are not part of the signal path. These are their own separate thing that are controlling basically any parameter in it. And with some sense, it can't be any parameter, but with some sense, it can be any parameter, like literally anything. But this is essentially the layout. This is the most reliable diagram that I can show you, and I can give you my seal of approval that this is kind of how a synthesizer works. But is this going to help if you pull up Massive or Serum or, Silent One? Are you going to be able to figure out how this works? I don't know. Maybe this might be enough. But if you pull up a Moog synthesizer, this will probably help you. This will give you the pathways to understand it, because a Moog synthesizer is, simple enough where you can understand it like that. But again,
if it makes you feel better, Justin, I have been sitting here while you're going through this diagram with my Arturia next to me, and I'm following along with what you're doing, and it is very, very accurate. So you did a great job with this.
Okay, thank you.
But yeah, just like you were saying, not to stop you in the middle of a comment.
I mean, this is the end of the lecture, so.
But I was just going to say that my Arturia, the amplitude envelope and the filter are actually reversed.
Yeah, sometimes that does happen.
Yeah, and you had mentioned that, and it's just built that way. Like you said, certain companies build their synths a certain way, and this happens to be one where you have a little patch bay where you can break those connections and you can reroute it. Mm-hmm. But at the default, right out of the box, those two are reversed. Right. And so you through patching and using those 3.5 millimeter cables, yes, you can break that connection and you can do something different. But yeah, it's this is great stuff. I mean, this is great. I'm sitting here. I had myself muted the whole time, but I'm sitting here making little patches as you're talking through it. So it's great.
Yeah, I hope this is, because the thing about synthesizers is like people hear all these terms and they're like, they open up a synthesizer and it's just a bunch of disconnected modules and
Yeah,
people are like, I don't know what this does or
right.
how it affects anything. So I'm hoping that explaining what everything is and then laying it out
Yeah.
is helpful.
I think this is going to be a good roadmap. And honestly, I think that anyone interested in this, Jensen, you're really the only one in the audience right now, but anybody else that's really interested in this type of work is probably best suited to get themselves a small setup, a small semi-modular like I have that
Hmm.
gives you all of these components in a laid out fashion, and it allows you to go through and build sounds. And then it allows you to, once you get comfy with that and comfy with the diagram that you have, you can then use patch cables to sort of do things differently and make it a little bit different. Really, the only way to get into this is to do it. You know,
Right.
these are great roadmaps and great places to start, but it's great that that's what's next. You know, that's awesome.
Yeah. So for the remainder of the semester, I think I only have 3 more classes that I can have time for.
Mm-hmm.
3 more weeks essentially. I'm going to go over additive and subtractive synthesis, and then the next week is going to be frequency modulation, so FM synthesis, and then like other obscure types of synthesis, like I can't remember the name of what I was going to say.
Granular.
Like granular, yeah, that's what it was.
Yeah.
Granular's fun, and then maybe fit in modular with that as well,
Mm-hmm.
and then take the last week to talk about like how to implement sounds, either actually implementing sounds into scenes in a movie or a TV show or a video game. So that's the general layout for the remainder of the semester. I wanted to spend more time on synthesis, but it is what it is,
Yeah.
this current situation. So
Oh yeah, it is. It totally is what it is. But great job. I can't wait to hear the next lectures. So I unfortunately have to run though, just because I hear kids like running around crazy
no,
upstairs. My wife's
no,
probably
that's fine. That's fine. If
but
unless you have any questions, this is basically the end of the lecture. I've been
no,
recording these lectures, so
this was great. Yeah, I plan on going back and watching last week's and then tuning in next week for the next one. So great job. And
okay,
I'm really, really enjoying it. So keep up the good work.
sweet. All right, thank you.
All
And
right,
if
Justin Jensen, I will talk to you soon. We'll figure out when we're going to meet soon once I look at that poll, but be well.
Yeah, you too.
Thanks.
Talk to you soon.
All right. Thank you. All right, Justin, take care, man. All right.
you too,
Thank you. Thank you.
no problem. All right, and Jensen, if you have any questions about this, this is the time to ask. So
Not, not really. I mean, it's kind of a lot to absorb.
it is a lot, and I'm going to send out this PowerPoint in an email. So, and the video, like I'll send out like the recording of the lecture again. So, yeah. So if you ever need to look back on it, so if you don't have any questions, that's the end of the show, ladies and gentlemen. Thank you for coming out, and yeah, take care. Next week we'll talk about additive and subtractive synthesis and get a little bit more in depth on those specific types of synthesis and what they mean and how to do them. And yeah, so I'll see you around, man.
All right, good night.
Good night.